Next, let's look at some methods for figuring out the values of those constants in the PI and D controllers. We call this parameter tuning. PID parameter tuning is fairly complex, right? So basically we have to find values of K, P, Ki, and Kd that lead to a good solution, that lead to a controller that is optimal for our case, that is not, that has a fast rise time, that's not underdamped, it's controlled, and it gets there quickly, it settles fast, right? There's a couple of approaches. One is the manual one, which is basically a kind of guess and check, and then we're going to look at the Ziegler-Nichols approach, which is a algorithmic approach to finding a good controller. It's not optimal. For that we need to do a bunch of calculus and stuff like that. I'm not a big fan of calculus. We're going to skip that part. Take a controls class or a mechatronics class if you're really interested. They offer them in the electrical engineering department. And you can go as far down the rabbit hole as you want. There is a lot of really interesting work in controls. I'm not a super good math guy, so we're going to skip that part. So manual tuning is basically the guess and check method, and we have a little table here that you can use to guide these things. And basically, as you increase any one of these parameters, these other parameters decrease, but they don't decrease alone. So this is the problem with manual tuning, is that if you have all three of the pieces moving together at the same time, the response times and rates of each of them in turn are going to have different characteristics. So as you're tuning them, you're actually changing the responses and the contributions of the other ones over time, and they interact with each other because they're affecting how the error is generated, and that flows down the chain of behavior. So for instance, increasing the proportional constant generally decreases rise time, increases overshoot, and doesn't really change the settling time. It decreases the steady state error, which is good, but it degrades the stability. It makes it more likely to oscillate. Increasing the integral constant decreases rise time as well. It shoots as fast as it can. It will increase overshoot, same as the proportional controller. It will increase the settling time because it'll take longer to oscillate down because of that accumulated error, but it can eliminate the steady state error, which is really positive. And again, it decreases the stability of the system. It's more likely to oscillate. The Kd, the differential constant, doesn't really change the rise time because it's only concerned about the delta error. It can decrease the overshoot. It can help bring down the overshoot. It'll decrease the settling time, which is really good. That's what we want. It doesn't really have an effect on steady state error, and the stability can improve if Kd is small. If it's large, then it can cause it to go swinging out of control because you're amplifying the change in error as it goes. It's a feedback system. So looking at that, and basically what we've been approaching before, basically what we've been approaching up to this point is manual tuning. We're kind of guessing and checking and stuff like that. And a good way to do this is to do one at a time and see if you can get a good set of values for each of them, and then you get close. You get a good-ish system. The Ziegler-Nichols PID tuning approach starts by searching the proportional values until you get a stable oscillation. This is what we call the critical constant, right? And then at the same time, and what that stable oscillation will look like is something like this, right? This is a simulation of a system oscillating over time, and you can see that it's just barely decreasing, but it's fairly stable. It's not decreasing very quickly, but this is relatively stable. And the next thing is, once we have this, we can measure the period of these pieces. So this helps us tell what the overall delay integrated in the system is, and stuff like that. So I want to measure the time between peaks of this oscillation. And once I have those two things, I plug it into these sets of equations for different good controller rules of thumb. So this is not optimal, but it allows us to get a good controller. So in this case, if we have just a P controller, a proportional controller, my KP should be set at half of my critical, constant, right? And that gives me a good proportional controller. Let's try that out in my little simulator here, right? So in this simulator, I've got a controller built into a system, a simulated system process, and as I change the parameters here, I can see what kinds of systems. So that's an uncontrolled system, that's too high. If I do 1.5, that settles down too low, so let's do 1.7. That settles down eventually, 1.75. Gives me something pretty stable. So let's call that my critical value. 1.75 is my critical value. For a proportional controller, 1.75 divided by 2 is going to be 0.875. And that looks like a pretty good proportional controller. It settles quickly, but it has that that proportional rise time that's not very good, right? So looking back at my table here, if I want to do an integral controller, I have my critical value, but I don't have a proportional or my critical period. So let's do 1.75 for my critical period, and it looks like that's between 12 and 31. So 31 minus 12, whatever these units are, it's 19 units or 19 time steps, right? So in this case, so my period is 19, my critical gain is 1.75, so my KP should be 1.75 times 0.45, which is 0.7875. Right, so that gives me a good proportional controller. And now I want to integrate the ratio between my critical gain and my critical period, which was 1.75 divided by 19. So that's my ratio, and I'll multiply that by 0.54. And I get 0.049. I'm just going to make it 0.05. In this particular version of the simulator, it's inverted. So I need to take the integral constant is inverted. So I need to take the reciprocal of this value, which is going to be this guy, which is about 20. Okay, so we do put 20 in there, and that gives us a good proportional integral controller. And similarly, if I want to do a PID controller, I do the same sort of work. So here I've got 0.6 times my critical period, 0.6 times 1.75 is 1.05. I want to do 1.2 times the ratio between my critical gain and my critical period. So it was 1.75 divided by 19 times 1.2. And because we're inverted, I'm going to take the reciprocal, so that gives me about 9. So I'm going to put 9 in there. So that's a big change in the system. We've made it very aggressive. So we want to tamp it down by taking these two, multiplying them, and chunking them through this little equation here. And that's going to give us, I want 1.75 times 19 times 3 divided by 40 is about 2.5. That's a pretty aggressive controller, right? So that gives us a little bit of oscillation, but it's a pretty aggressive controller as it gets in there, and that's pretty rough. That's going to be pretty rough. It looks like it's pretty high. We might want to see if we can flip that. So if I take the reciprocal of this, 0.4, that doesn't help at all. Yeah, that gives us a little bit better, a little bit nicer settling time, but it's still pretty aggressive. In the ideal case, we'll end up with something that looks pretty stable, that has a very quick rise time, a very fast settling time, and doesn't oscillate very much. Again, this is just a rule of thumb. It's not terribly much better than going through the process of just doing manual tuning. You can often do better, and you can see that our system was actually, this particular system was actually more stable in the PI configuration and had a smoother response than it did in the PID system. So sometimes you don't need the D part. It's the derivative part often doesn't contribute much, so you can skip it and make the simplest possible thing that works as best as it can.